it is my great pleasure to introduce the first speaker of this session, Marc Russwurm, who is an assistant professor of machine learning and remote sensing at Wagendingen University, and he will talk about Earth embeddings. Marc, the stage is yours.
All right. Thank you very much, and thank you for interrupting your conversations and your nice lunch to come inside again. It's a pleasure to be here and to talk about this line of research that I think nicely complements a lot of the species distribution modeling that we've seen in the keynote so far. But I want to focus a bit more on a technical level, what we can do with remote sensing and geospatial data in general to extract patterns from the images that go a bit beyond image encoders per se. Yeah? But let's start with a small game, because why not get active again? I took this image from somewhere. Where do you think that image is from? High-resolution satellite image. Is it A, somewhere in Spain? Is it B, Netherlands? Wageningen, maybe? Is it C, somewhere in Switzerland? Who's for A? A few hands, good. Who's for B? Good. Who's for C? Yeah, okay, it's number 3. It's a trick question, right? Because it's Zurich, yeah? But what we play here is we play GeoGuessr, if you know that game. Where we have an image and we try to locate it on a specific place on the map. And if we think a bit deeper what we do when we play this GeoGuessr game and we solve this geolocalization task is we analyze visually that image. So we see a lot of patterns in that image, descriptors, you've heard this morning, like regular city blocks. We have some gabled slate roofs, dense housing, etc. But it's only one part of this geolocalization game. The other part that is equally important, but even maybe more exciting, is the mental or the idea what is behind a certain location. Because we have a lot of contextual information from us basically navigating this world and our mental map. And we can put that image into context, and we can say, like the city blocks look very Gründerzeit-ish, so it's at least mid-19th century. It's a mid to large-sized city. It was already that big, that long ago. And we can also see the remnants of a citadel in the channels, in the streets. So there's a lot of additional context information that we bring into the game when we play this GeoGuessr or this geolocalization game. And that's an interesting field in terms of encoding geospatial knowledge into some system, in terms of, in this case, a neural network. But what we are doing in general is we ask the question how to describe this place. And if we think about it from a classic data science, environmental science, remote sensing perspective, we would say with all data we can basically come up with. So we can describe this image or this place by text, we can install sensors for temperature, we can estimate the elevation, etc. But there is more information in that image that we can extract, because we can also think about it in a more implicit way in terms of what specific patterns that are visible in that image are there that make that place unique. And if you can formalize this way of extracting uniqueness from readily available open remote sensing data, I think that's a very powerful idea. And what we can do is basically extract an embedding vector that puts that uniqueness idea into a metric embedding space where we can then calculate similarities between different places, for instance. And if you would want to model this geolocalization game with in machine learning, we can formulate it as a retrieval problem. Use an image encoder to get like visual type of patterns with a CNN. We can use a location encoder, and I'll go into that in the second part in depth, to get a vector that describes that location semantically, but only based on the coordinates. And then we can put that together and we can make a retrieval question and find the nearest neighbor basically of these two vectors. And these three parts are basically the three parts of my talk today. So we'll go briefly over the idea of extracting descriptors, features from pure remote sensing images with remote sensing foundation models in the first part, but enough people have talked about that also today. Then I'll jump a bit more in the idea of implicit neural geo-representations, where we have a new way of using neural networks in terms of not encoding like discriminative patterns, but in terms of storing information in neural network weights instead of like discretized raster and vector data. And then at the end, we bring it together, and I'll talk about a work called SatClip that was also mentioned this morning that trains both of these encoders together. Good. So let's get started with the first part, pre-computed embedding fields. So you may have heard of remote sensing foundation models. There's plenty of discussion what they are, do they entail. But in a nutshell, what we can see is they use a lot of different remote sensing modalities, optical data, radar data, JEDI data, like LiDAR data. And what you can do is you can extract basically descriptors, features from these pre-trained remote sensing foundation models. And what has come up now quite a bit is the idea that a good remote sensing foundation model, if you freeze it and you don't train the remote sensing foundation model and you only train the individual task heads that are really small, that this is like a fairly powerful way of using these models because you don't need to deal with large models and large multimodal models. And also what you can do in particular, you can download the large geospatial data, put that through this foundation model, and then you can store again these descriptors in the same database, for instance, as a raster. And then you can only do, you only have to do linear regression on basically these pre-computed features that are already there. So that is a big plus in terms of usability because for an ecologist or a marine scientist who don't want to deal with big deep learning models, they can basically just download features from a database and use them. And that may sound quite familiar because large papers recently came out, like the Alpha Earth model from Google, which does exactly that and stores like these embeddings in Google Earth Engine. Ready to use. There's others as well that are available that basically do a compressed view of the remote sensing data that we have available. And these embeddings can be quite helpful, especially for domain science tasks where there's little data. So I want to give you this one example from our student in Wagendingen on tree national forest inventory, which is quite a tedious task in terms of annotating which tree species are growing where people go into the forest, they measure the basal area and record like all that information, and ultimately nationwide you get data sets of like 1,500 basically points where these trees are growing. And classically, that's a fairly small data set. You could not easily throw a random deep learning model at it, but with pre-trained models, you may get a bit further. So what we can do is we can take remote sensing data, so monthly Sentinel-2 and Sentinel-1 time series. And classically, what related work has been doing since a while is basically fitting several functions to this time series, like harmonic functions, creating a feature vector that way, and putting that through a random forest. And now with like pre-trained deep learning models, we can use, for instance, the Presto model to get these deep embedding features. And what we did in the study is basically compare how much accuracy benefit do we get just basically on using these embedding features. So if you think about it, nothing crazy. We downloaded that image, forwards inference, and then put it through a random forest. And there's 4 to 10% accuracy increase just in using these deep features compared to basically these hand-defined features. And the reason is basically forests don't grow in sinusoidal patterns. So the idea of fitting sine curves to red, near-infrared, etc. channels is just not really catching up well with reality, while the patterns that are extracted from Presto are actually better for the task in particular. And we can take that one step further, of course. So if we to put in the effort, and we also train the Presto model additionally on the data, and we fine-tune it, we get another 1 to 4%. But the main benefit basically comes from these deep features, and that we can just use plug and play, like in these big foundation embedding databases like Alpha Earth, etc. Good. So that was the first part. We can use remote sensing models, pre-trained models, to get these embeddings that extract like patterns from those images. But it's basically like our example in the beginning. We have the slate roofs, we have the corners, we have the shapes, but we don't have really the context, the context that we know about the Gründerzeit and about the history and all of that. So let's jump into the second part in terms of how can we give location a semantic meaning by basically putting data into neural network weights. And we enter this field of implicit neural representations. And the core idea here is that it's not a field that is it's a field that is emerging, basically informed from disciplines like computer vision. You may have heard of neural radiance fields, where you have a 3D scene, and then you have different pictures from different perspectives from this 3D scene, and then you can train this neural network that inputs the coordinates and the angle, basically, of the ray in which it is pointing, and to just basically output the RGB value of this individual pixel. And if you do that long enough, you encode this 3D scene information not as like voxels or polygons, but you encode that in the parameters of the neural network. And what we can do is we can take the same idea of encoding our geospatial information also in the parameters of a neural network in one way through supervised learning. So we can define this neural network that imports coordinates. So that's all that it's doing. It has longitude, latitude. Sometimes we can also input time. And then it outputs a value at that particular coordinate. And if we have a ground truth, and I'm showing you like a very simplistic land-ocean classification problem here, we can then basically define the loss, adjust the weights, and this model will, through gradient descent, start to basically approximate the function of land and oceans with 0 and 1. So in supervised learning, we can see that more as a interpolation type of approach, where our network weights start to learn this geospatial function on the sphere. And this type of line of research has been used quite a bit in species mapping or species distribution mapping. So here's one example from Elijah Cole on iNaturalist with their SENA model, where they have this neural network, the species range model, inputting coordinates, and then basically predicting the presence of 0, 1s of the species. And what you can see is basically after you train this model and you predict with other test points basically in a grid, the model will smoothly interpolate between those different point observations and also give you a continuous probability map. And what they showed nicely in some analysis here is that when you take the encoder, so some embedding or some feature representation in the middle, and you do a PCA map on that, you will see also that these embedding dimensions or feature dimensions roughly correspond to like mountain ranges and biomes and biotopes. So this idea of moving implicit neural representations from fields like image processing or 3D mapping to the geospatial science is already quite there, especially on iNaturalist, which is driving this quite a bit. And there's a nice review here from Genshin Mai, who summarizes nicely that when you build such a location encoding model, basically it makes sense to put it into 2 modules. The first module is this positional encoding, which does not have any trainable parameters. That basically puts the coordinates into a higher dimensional representation, so there can be sine and cosines, for instance. And then you use a neural network with a few layers to then store the information that you want into this neural network. And what we investigated especially a bit more is going not with like sine cosine basis functions as others, but we go for spherical harmonics, which has been used in the earth sciences quite a bit. So for instance, for the Earth's gravity field, since like decades, we encode that as a combination of linear spherical harmonics. So here you don't see basically the harmonics themselves, but there's different frequencies the further you go down. And the idea is quite similar to like a Fourier series, that you can encode any function on the sphere with basically enough spherical harmonics in this linear combination. Good. Then from computer vision, there's also a second idea that has spilled over into like the geospatial location encoding science, is that if you design a neural network, usually we would use ReLU activation functions, because for classification we want to zero out patterns that are not particularly relevant. But for encoding like information, like in this case the RGB value of this of pixels in this video, it makes sense to put sign functions as activation function. And the reason is quite connected to Fourier series, that if you have, there's basically multiple Fourier series stacked on top of each other. So one takeaway here from like the Sitzmann paper, which is a nice read, especially for this idea of storing data in neural networks, is to use sign activation function in these cases. And that's basically what we did in our iClear paper last year, to bring together both of these worlds to look at the location encoding networks. We evaluated them quite broadly. And then propose a new location encoder that has spherical harmonic basis functions that are well defined on the entire sphere, and not only like on the equator, but also on the poles, and then combine that with sinusoidal representation networks, while a lot of related work, especially who were working more on the species range, they used mainly ReLU networks. And that was our okay, sorry, that doesn't render particularly well. But one idea here is that with the spherical harmonics, we can control basically the smoothness of the function. By basically increasing the number of harmonics, we get a higher resolution signal that we don't see on these plots, unfortunately. But another quantitative result we have from this iClear paper is we compared a lot of different positional encodings that were proposed in the previous years. So there was a whole line of different ways to put sine and cosine functions in different configurations. And we compared basically with a ReLU network, the FCNet and the SerenNet, with sign activation functions, and we tested on iNaturalist, and we measured how good does the location information additionally add accuracy on image classification. So when you see plus 9.3, it's like 10% more accuracy if you bring in the location information. And what we see is just putting directly the coordinates into a model is okay, but is not best, especially for the FCNet, you are 2-3% lower. For the SerenNet, it doesn't matter that much, but I come to that a bit more. But when we use spherical harmonic basis functions, which are just really well suited on the sphere, we see that the actual choice of the neural networks doesn't matter anymore very much. So you can use a ReLU network, or you can use a Seren network. It's fairly similar. Even the linear combination, like we do in geodesy since quite a while, is also relatively good. And simultaneously, what we see is that the Seren network, so when we use a location encoder with the sign activations, we may not need the spherical harmonics or like the positional encoding in the first place, because what we show in the paper, and I'm not going in here, is that the Seren network basically can learn these positional encoding functions basically by choosing the right weights for the first layer. Good. So takeaway from this deep dive into implicit representations and location encoders is, if you want to integrate coordinates into any model, it makes sense to use sign activation functions, sirens, and if you have data on the poles where the spherical geometry matters a lot, then spherical harmonics are a good choice, because sine, cosine functions, you start to get artifacts on the poles. Good, but the larger takeaway of that, beyond the individual paper, is basically we're moving away from storing data in explicit discrete forms in terms of databases and points, lines, polygons, and rasters, towards we store a continuous field of geospatial variables in weights of a neural network. So currently those neural networks are fairly small and the resolution is fairly low, but we can work on that down the road. But it's it's a different way to think about our geospatial world, because our world is not discrete, but still we discretize it into points and vectors and polygons. Having a representation in parameters is an elegant way to also capture this continuity of our world. Good. So we looked in the first part on foundation models and extracting patterns from images. We know now how to build such a location encoding model that inputs coordinates and outputs us a value at a specific place. Let's put it together. So now we can start to really go beyond the supervised learning and have interpolate between different data points and actually input it into a self-supervised contrastive framework. And that's basically the part 3, geolocalization as training objective that we followed in the Sutcliffe paper. Good. And the idea is basically that we have a lot of geospatial data, and all of this data has a coordinate. So that makes it geospatial. So, and we can get basically terabytes of that data easily. And what we can do, in this case for images, but the idea goes quite beyond, is you can put these images through this image encoder. We looked at that at part 1. We can look at the coordinates, put that through a location encoder. And then we have these 2 vectors, and we can basically train it together with contrastive learning and the CLIP objective. And sounds like yet another application of CLIP on another modality. But I think something really interesting is happening here in the geospatial case, is because we basically train this model to, given this set of images, give you the most likely coordinate that image is coming from, and vice versa. Given this coordinate, give me the most likely image that originates. And what we can do then after it's trained is basically, we are mainly interested here in the location encoder, is we can use that fairly small network and then create an embedding continuously for any coordinate that we can input basically on the Earth. And that's, if we put a PCA, we can create these types of plots where we see nicely that they correspond to biomes, biotopes, mountain ridges, etc. And in particular, places that are distant but have a similar climate, they have similar PCAs, and vice versa. And the intuition I want to stress again, because it goes a bit beyond, is that there's a lot of implicit parameters that we have behind our remote sensing data that we are not explicitly measuring, but we can see the effect on the representation of these images. So population density, soil quality, precipitation, biodiversity, so a few more, a few less, but there's a lot of information in these images. And by putting them through an image encoder and training together this image and location encoder, the location encoder implicitly encodes a representation of all of these factors that determine what makes these places unique as a training objective. And then we can use that parameters of this MLP as a starting point to solve a few downstream tasks like predicting population density and so on. And one big benefit here is on the usability, because after it's trained, it's basically just a small MLP. You can download it easily. It's a few layers. And it can be easily integrated in another neural network to give location, not only the information of, okay, this is east and west, but actually give an environmental representation of this location to another downstream model that you want to integrate in. And some obvious examples here. So if you want to generate images of remote sensing images, it makes sense to condition it in the locations because in this case, houses look differently in different continents, so that's pretty obvious. So if you have a generative model, it makes sense to bring in this environmental and these parameters into this model in an elegant way through, in this case, pre-trained weights of the Sutcliffe encoder. Another work from colleagues at DLR is basically super resolution. So it's a similar idea where you If you want to super resolve the Sentinel-2 image to high-resolution images, there's obviously a lot of fine details that can be different, but those differences can be narrowed down quite a lot if you know the place or the continent or the location where you want to super resolve these images. So that's another recent application of SATClip. And for species distribution modeling, I think we've seen an example this morning as well. And SATClip is not the only one, so there's also similar works with pre-trained models in this case available. For instance, GeoClip is really nice. They used ground flicker data, and they align that with clip, so the text clip. So what you can do then is basically have a bit of a text query and like see which embeddings are more aligned with the word desert. And a logical next step is then combining basically both embeddings. So using the more low-resolution location encoder embeddings to then retrieve high-resolution image embeddings or images more dynamically to then improve the resolution. In this case, again, for more tailored towards like biodiversity and species mapping. Good. So that's the three main parts. So we looked at the image encoding part, at the idea of encoding geospatial data in network parameters, and then using that beyond pure interpolation, more in a geolocalization task to really answer the question of what makes this place unique. But I think it's a bit part of a larger kind of shift in the idea of how we think about geospatial data. So in the first part, we were all moving within this discrete geospatial database world. We have geospatial data layers and data cubes that you can retrieve. You can have a big backbone foundation model, get embeddings, store that again in a discretized way in the same type of discrete database. In part 2, we looked at neural networks to encode data in general, and then in part 3, we looked at the continuous, the way to output basically embeddings from this neural network way of storing continuous embeddings spatially that only input the coordinates. And when I look a bit at the literature, there's obviously plenty of foundational GIS infrastructure knowledge on the left side here in terms of how to work with geospatial data. There's obviously a lot of like emerging foundation models that are there for image and multimodal image encoding. But what I'm focusing on a lot with like more recent research is this, I think, new idea of encoding geospatial data in general in a continuous form through neural networks. I think where we are scratching the surface at the moment. And obviously, they are much more low resolution than these image embeddings, but we can work on that, increasing the capacity, doing some retrieval augmented generation, etc. Good. With that, thank you very much. I still have 2 minutes for questions. That's good. It's obviously not work alone, so you have plenty of people below. If you want to have a deep dive on location encoding, I have a 45-minute talk there as well, and I'm happy to take more questions, and I'm around as well.
Okay, thank you very much, Marc. I can already see one question.
Thank you for the talk. I'm wondering, with regard of application of those foundation models to the ecological questions, do you know of any works that are investigating the transparency of the or interpretability of the results? Because as an output of foundation model, we basically get an embedding of somehow mixed remote sensing and geolocation and maybe other predictors. And the question is, like, what actually was the driver there?
So if we can, let me rephrase a bit. Maybe if we can map back like this more abstract embedding space into like the underlying variables that we are encoding. I think that's a very good area. I think one way to, like, obviously. We're going the opposite way here at the moment with like the encoding. But if we go for a more retrieval augmented augmentation approach, where we use that to then query data dynamically, we can use basically this query as a way to emphasize which data is most relevant for this location and for this task. So let me give you one example. So at the moment, when we look at these embeddings a lot, we see that different models are differently good for different tasks. And we only see that based on downstream performance. But if we can basically build a system that dynamically queries embeddings and underlying data, we can then retrieve back which underlying data is most relevant for the task and then get a bit more feature importance that way. Yeah? And I'm thinking that's something to bring both of these worlds together a bit more.
Thank you very much. Is there a very short question? Okay. I have questions, but they are not short at all. So let's thank Marc once again.
Thank you very much.